Okay.
I'll ask you a question later after finish.
Please go ahead and ask all the questions you want on assignment 1. Also for Muhammad, the same thing. If you have any questions on assignment 1, please do that so that you can actually get the answers on the recording. So go ahead, Abdullah.
On the lecture, we used the formula with 256 over 2 over 2 to the power bit without minus 1.
Yeah, actually, it's going to be the same. But actually, if you want to have it as, for example, let me. Basically, if you want to have it as an 8-bit image, okay, the 8-bit image will have to be from 0 to 255. So this 255 is 2 to the power 8 minus 1. So if you want to have it as n-bit image, which is a quantization that is general, okay? So it's going to be from 0 to 2 to the power n minus 1, okay? So basically, this is the right way to do it. If you do it with 2 to the power n, it's going to be fine, but you're going to have a problem with the maximum. It's not going to be 2 to the power n, because actually 2 to the power n is going to be higher than the range that you have. If you have an 8-bit image, it's not possible to have a grayscale value of 256. The maximum is 255. So basically the correct way to do it is to use 2 to the power n minus 1.
Okay, fine.
And the same thing I was saying to Reno a few minutes ago, if you have image minus minimum over image, maximum minus minimum, okay, this will normalize the image to basically, it's going to be from 0 to 1. But the point is, if you have your image here as integer, and the minimum here is integer, and everything here is integer, the problem is whenever the image is less than the maximum, this will be basically 0, because basically this is an integer division, okay? Any integer division where you have, for example, if you have 200 over 256, this will be 0 as integer division. So actually we don't want that, okay? So basically the way to do it in order for you to get something that doesn't become 0 all the time, basically instead of just putting image here, just put double of image and leave everything the same. So replace this with that, okay? Just as a solution. Basically, when you take that and multiply it by this number here, you will get the quantization that you want. Okay? This is problem quantization, basically. Okay?
I made, Doctor, as the same in the lecture. I made double and I used the unsigned integer.
Unsigned?
And the result will be okay. Or it's okay.
Okay. Okay, great. So do you have any other questions in the assignment? I had some questions from Anas. Anas, your colleague. I'm not sure if he's here or not. Anas, Anas is already here. Basically, I just wanted to point out that don't worry about the, basically if you understood something from the question that I didn't mean, or basically if you, basically if the language of the question basically was basically, there's basically two different interpretations. It's acceptable. Either of them will be correct, basically. Don't worry about what I mean, okay? Whatever you understood from the question, it should be fine, okay? So don't worry about it, okay? The most important thing is just to see that you can do whatever you want, okay? If you told me that I will do this, you do it right, this is the most important thing. Okay, even if
Thanks.
it's not exactly what I wanted you to do. Okay, should be fine.
Okay, thanks.
So any other questions regarding the assignment?
Doctor, I have notes.
Go ahead.
Doctor, I tried to the power n minus 1, and also I tried the 2 to the power n only. I
Okay.
found different between them in the vector. I
Yes.
think 2 to the power n minus 1 is less construct from the other, but I don't know why.
Basically 2 to the power n, if you're using an 8-bit image, okay, 2 to the power 8 is not a part of basically an 8-bit number. So basically, if you have a 256 number, if a number is 256, it's going to be 0, okay? So basically, you're going to have a distortion related to that. If you're trying to put 256 inside 8 bits, it's going to be 0. It's not going to be 255, okay? So this will be a problem. So 2 to the power n minus 1 is the correct one.
Okay.
Okay. Okay, so let's just go over the lectures, the topics for this lecture today. Basically, I'm going to show you how to simulate noisy images. So basically, we're going to take a regular image, and basically, in order for us to be able to test filters, we're going to create noisy images with different noise levels so that we can test the filter performance and basically think about what to do for different noise levels and different noise types and things of that sort. Okay, so this is the first thing that we're going to talk about. We're going to talk about linear two-dimensional FIR digital filter, which is basically what we did last time. We're going to see some more example applications. And basically, I'm going to talk to you about basically how to think about the design of the kernel, how to design a kernel that fits a particular problem, and the difference between different kernels. We're going to do some more experiments using image filter and F special, basically, and how to create the custom kernels, basically, depending on the application. Then we're going to move on to talk about nonlinear filters. Nonlinear filters, basically, I'm going to choose a very particular and very useful type of filters, which is called morphological operations. And basically, we're not gonna cover all the aspects of morphological operations. We're gonna talk about some of the most important parts of it, which is basically how to do image dilation, image erosion, image closure, image opening, and basically how to design the kernel that we're going to use for nonlinear filters in a similar way to that, the one we used in the F special in the linear filters. And also we're going to do basically see some application different image types. And if we have time, we're going to start talking about the Fourier transformation of images. And basically we're going to talk about it in the context of MRI K-space, which is basically the domain of MRI data acquisition, so that we get basically to the last part of research problem 1, which is related to MRI image reconstruction. So basically, these are the topics that we are planning to do today. What I'm going to do now, first of all, we have the Maghrib prayer now is very early. It's about 6:15, something like that. So what I would suggest is that we break at 6:30. And basically, we start, basically, we pray and then we come back. And next time, I suggest we start at 6:30 rather than start at 6 and then break after half an hour. Would that be okay? Let me write it down here. So basically, suggest change of time.
Maybe start earlier.
Basically, we want to basically instead of having 6, we'd like to start at 6:30, so that we pray Maghrib before we start, so that we don't have to break in the middle. Would that be okay? Because Maghrib is somewhere here. Maghrib is 6:15 now. Maghrib is now the Adhan is right now, basically. So basically, if we start at 6:30, we don't have to break. We can basically, we don't have to break. Basically, we can take the full lectures without break. Would that be okay with you? So that we don't have to break after a short period of time after the start?
I don't
If we
have any
start
problem.
on 4, is it possible? Okay.
I can't hear you. I'm sorry. Can you repeat?
Is it, if we can start on 4 maybe
4?
earlier? Yeah.
Yeah, it's fine with me actually. Next week it's fine. I don't mind at all if you start at 4:30 probably because of.
4:30.
How about that? Do you agree? 4:30? Would that be okay? I need the approval of everyone. We cannot have someone with a problem with this time. You all agree on that?
I don't have problem.
You have a problem? You have a problem?
I agree.
No, I don't have. It's fine. It's fine with me.
Okay, so it's fine with Muhammad. So how about Abdullah?
I agree.
You agree also?
That's fine.
Okay, Anas?
Okay, it's fine also with me.
Okay, so next week we start at 4:30 inshallah. Okay. From next week we start at 4:30 to 7:30, okay? 7, no, not 6:30. About 6:30, okay? So we start at 4:30 inshallah, okay? I'm going to send an announcement anyway just to make sure that everybody got the basically got the information, and I'm going to change the time in the Blackboard Ultra. So it starts at 4:30 inshallah. Okay. So how about if we break now for the prayers and we meet at 6:30, 6:35.
Okay, no problem, doctor.
Okay. Okay.
Okay, so let's pray because actually the adhan is right now, so it doesn't make sense to start the topic and cut it off after 10 minutes. So we're going to break now and come back at, let me write it here so that it's clear. Okay. That be okay?
Yeah. Okay. Okay.
Okay, so let's do that. Okay, so I'll see you at 6:35 inshallah. Okay. Okay. Assalamu alaikum. Assalamu alaikum. Are you all back?
عليكم السلام ورحمة الله.
Yes, yes,
Salam.
Okay. So let us review a little bit about what we talked about last time about spatial domain image filters. Basically, we talked about having a kernel that looks like this. Can you all see the presentation?
Yes.
yes, you can.
Okay, so basically you have a kernel that has A, B, C, D, E, F. Basically, these are the numbers inside the kernel, okay? And this is the original image matrix. Basically, you have numbers here like A small, B small, C small, and so on. If you want to compute the element in the middle here, all you have to do is center the kernel around that point and basically multiply the value from the kernel to the value from the image and basically have this summation over there. So basically have AG plus BH plus TI here. See here, A is multiplied by G, B is multiplied by H, C is multiplied by I, and so on. And basically have the summation over the total of A plus B plus C plus basically the summation of the elements in the kernel, so that you basically have a normalized version. You don't have a multiplied version or an amplified version, okay? Imagine, for example, if you have all ones here, basically if you do that, then you're going to have the element in the middle here will be basically the summation of all elements here. You don't want to have that. Basically, you want to have it as the average of the elements around it. Okay, so basically compute this, and basically in the resultant image, the value of m dash here, the value that used to be m here would be m dash, and this m dash will be calculated like this. You design this kernel to perform the function that you want. You can have a function that basically targets average. If you have noise, then average is usually very useful when you have noise. You might want to have another kernel for edge detection. If you have an edge, you would like to have a kernel that would be able to detect an edge or do a differentiation, something like that. So basically, there are so many different ways of doing that. One way we saw last time is to use f special, which is a function that allows you to design a kernel for a particular application. Okay, but here, basically, this is in general, you can design this kernel the way you want. Okay, I'm going to show you some examples now about how to do that. So go to MATLAB. This is the code that we used last time, basically, and we use image filters here. Let's just remove the part that has the DICOM and DICOM info and things of that sort, and the histogram. We had a part that talked about the contrast enhancement. Let's start with the image filters, okay? Let's get this here, okay? This part here. Okay, I don't have to do that. Maybe I'll start the code here with it. Basically, okay. So this figure 1. Basically, I have a F special here. Let's see the help for it. Sorry, not this. I want to have the help for it. Help is F1. Okay. So you have different kernels that you can actually generate, and each one of them has a different shape. And I'm going to show you how these look like. We talked about Brewitt and the Sobel. Both are actually kernels that are intended to detect edges. Okay, so you design a kernel using F special and this particular choice of F special, and then use image filter with the filter that you designed, basically, in order for you to be able to do the filtration that you want, okay? And if you transpose this filter, if you basically make the rows columns and the columns rows, you can end up with vertical edges instead of basically horizontal edges. What I'm going to do now is, instead of doing this, I'm going to design it myself, okay? So I'm going to say that, let's go and discuss it first on here. Basically, imagine that you have an image, and this image basically has, let's just draw it this way. Okay, you have an edge here. You have an edge somewhere in the image here, and this is, for example, this is one side of the image is black. So basically, this is here black. And this one here is white. Okay, so there is a very clear contrast between this side and that side here. Okay, and you'd like to detect that particular line here. You'd like to detect the edge of the black area or the edge of the white area. Okay, what we said last time is that we need something that would do differentiation. Okay, the differentiation basically is as we said before, in the regular or the continuous time, basically if you have dx by dt, it's by definition limit of f of, let's just forget about x of t plus dt minus x of t over dt when dt goes to 0. Okay, so this is the definition of the differentiation in the continuous time. For the case of basically this is continuous time. Of course, in the image we have discrete time, and in discrete time you have different differentiation formula. Basically, instead of the differentiation, we replace the differentiation by the difference. Okay, so basically here you have a difference operator, which is basically just a matter of maybe we can just say that it's x of n minus x of n minus 1, and that's it. Just a difference operator, that's it. Okay, and basically here you assume that dt is the smallest value of 1, because actually you cannot have dt, a difference in time that is smaller than 1, because basically we have the time going like n equal to 0, 1, 2, 3, and so on. So a very simple subtraction will give you actually something that is related to differentiation, basically. The one we saw last time, if you remember, basically we saw this kernel right there. The pre-weight kernel looks like this. You have minus ones here and plus ones here. If you see what this does, it basically, if you have this element here, if you are standing in the middle, basically you're taking the value to the right and the value to the left and subtracting them. If you are somewhere where the grayscale is exactly equal, this will be 0 basically. It's going to be the same value in both cases, and basically it's going to be 0. Let's try it here and compute it ourselves. Let's have, imagine that you have a kernel that looks like exactly like the SOPL, the pre-width, okay? And then you have an image that is all, for example, 9s. Any value, doesn't matter, actually, by the way. Okay. And basically, you want to apply, this is a SOPL, basically. This is a SOPL. This is a pre-width, I'm sorry. Actually, SOPL is very similar. Okay. So try to apply this to that. What you do usually, if, for example, I wanted to compute this element here, what I do is just put the kernel right there. Sorry. Better use the basic. I'll put the kernel here. And then do the calculation that we basically discussed a little bit earlier. Basically, imagine that these are, this is A. This is A, B, capital C, D, E, F, G, H, I. Okay, and these are the basically the numbers that are there. So basically, in order for you to compute this value here, it's going to be basically A times 9 plus B times 9, because basically they are all 9s, and so on, okay, until I GHI times 9 over the summation of all elements here. But actually here we cannot have the summation because the summation will be 0. So basically you're not going to do that. You're not going to divide by anything. If you do that, you will find that basically you have a summation of all the elements here, A plus B, and so on. If you don't have a summation, the summation of all the elements here multiplied by 9, which is going to be what? So the summation here is going to be what? 0, right? So this here will be 0. The outcome here will be 0. And basically, if you move it anywhere where all the values are the same or very similar, then the outcome will be 0. Imagine that you have now an edge here. For example, if you have here, for example, 5, you start having 5s here. Then there should be an edge here somewhere, right? So if you take this kernel here, just imagine that you move this kernel and basically you try to compute this value here. So basically you're going to have the kernel basically sitting here, right there. Try to compute now. What's going to happen is that the summation will be what? Basically this, all the elements here in the middle column would be basically useless because they are going to be multiplied by zeros. But the difference between the elements here will actually sum up to a number. So for example, here we're going to have -4 plus -4 plus -4 plus all zeros. Okay, 3 zeros. Okay, so basically you're going to end up having -12. So the result here, the new result here will be -12. -12, actually the result from the Brewitt, anything that detects the edges or detects the does differentiation, we really don't care about the sign here. The sign doesn't really matter because basically we care about the magnitude more. Okay, a negative sign would mean that a transition to a lower value. A positive sign would mean a transition to a higher value. But if we care only about the transition, then the negative and positive are the same. So basically this can be used to do that. But the problem is, do you see any problem here, by the way? Do you see any problem with using the Brewitt kernel right there? Basically, you're going to have here in this column, if you apply this kernel here, or you lower it down here, one element. So basically, all the elements here will come up with -12 in the output. So basically, this will be -12 in this particular column. If you put it here, if you put the kernel, basically, instead of having the kernel here, imagine that you put it here. Just shift it 1, okay? You're going to have the same exact thing because actually the difference will be exactly the same. So basically, you're going to have -12 here also as well. So there's a clear problem here in that instead of getting the edge only, basically in one element only as the edge, you have 2 points. Because basically these 2 points, these 2 edge points, the one that is at the edge of the 5s and the one at the edge of the 9s will be both basically -12 or will be both, having higher values or large values. How about if we design another kernel that basically doesn't do that? Instead of having the 0 in the middle, what's wrong with having only a kernel that looks like only -1 and +1? That's it. If we have it like this, then only the point in the middle here will basically be of value. Basically, there is nothing else basically there that can be basically -12. Basically, if it's here, there's 0. If it's here, it's going to be 0. Only when it's here, it's going to be -4. So basically, instead of having 2 points as edge, it's going to be only 1 point. One more thing. If I'm detecting the edge here, imagine that you have an edge that looks like this. Okay, you have here 5, 5, 5, 9, 9, 9, 9, 9, 9, 9, 9, 9. For example, if you have something that looks like this, you will have a problem in that the kernel basically will look at something that looks like this. Even though here should be an edge, it's a very clear edge here, and here it's very clear edge here, and here it's a very clear edge. It's not going to detect that because actually you're not computing the edge only in one row, you're computing the edge in multiple rows together. You have 3 by 3. So basically here you're not only computing the edge in this row, no, you're computing this one, and this one, and you're averaging them, you're adding them together. How about if you have only one row? We can do that. Okay, so basically it's a matter of design. So what we're going to do now is instead of using the 3 by 3 kernel, what I'm going to do here is I'm going to design my own. So basically I'm just going to start with something that looks like 1 minus 1. How about that? Would that work? Actually, it should. Okay. In order for us to be able to see the difference, let's have this H1 and this H2, and basically let's just forget about the dash for now, the vertical and horizontal, because actually it's a matter of just reversing the or transposing the filters. So I'm going to have here H1 and H2 so that we see the difference. Let's try that. Oh, we don't have an image. Okay, let's choose an image. What type of image would it? Maybe one of the images that we saw before. Maybe we should open again the MATLAB. I think it's C. Just choose a nice image that would show the images. Okay. Let's see. What type of image? Okay, there is one of the images that I remember with the spine name. There is a spine.tif, one of the images here, spine. I saw. Basically, it's here right there. It looks actually very nice. It might have some nice edges here between the background and the actual image. So let's load that. So just close that and basically start with reading the image. As we know from last time, basically it's as long as it's in the MATLAB folder, we don't really have to specify the directory where it is. So that should be enough. Okay, I'm not sure what we have here. Image adjust, image F2, image F plus. Okay, basically, I'm sorry. Basically, we added them together here, which is not really right. I'm not sure we should do that. We really don't need to display the third one here. And I think the one we have is the Sobel or the pre-width filter actually is probably in the horizontal direction. So basically, I'm just going to transpose that so that we can see similar directions. There's a problem here. Oh, okay. These are missing. Okay. Do you see any difference? Basically, this one here is the one that uses pre-width. This one here is the one that we just created now. Do you see any difference between the two? Any similarities or any differences that you can point out? Basically, if you look closely here, maybe it's very difficult to probably see it on your screen, but actually I can see it here. The thickness of the line here is thicker than the line here. The lines here are a little bit basically thinner. So maybe the edges are more well defined here than here. This is the one that we created using -1 and 1. Okay. But the point is, I think this one is a little bit noisy. See here, this part here looks a little bit noisy because basically there is an averaging effect. You try to, when you average the edges or the differentiation in 3 columns or in 3 rows, basically you're getting something that has less noise. Okay, so basically there is an advantage probably to using the Bray-Weight filter, but actually if you need a much more well-defined edge, probably the one that we just designed might be a little bit better. Do you get the idea? So basically whatever number we put there will basically determine what the filter will do. Okay, and basically you can design the filters very freely. You can just put an array, any array of any size you want, and basically this will be the filter that would be used. You're basically designing the values in this kernel here, whatever you want. Okay, one of the designs that we saw, basically if you use average, basically if you have all ones here, it's going to give you an average filter. I'm going to try that with you a little bit, you know, in a second. Okay. There are some of the similar filters to the Bray-Weight, which is one of them is the Sobel. The Sobel actually, instead of having the filter as just -1s and 1s, basically it has, one of them is 2. So basically, let's just look at the one here. For example, this is the vertical edge. You have 1, 2, 1. 1, -1, -2, -1. The idea from the Bray-Weight filter or from the Sobel filter is to emphasize the middle row where the point I'm filtering is residing. Okay, so instead of having the same value or the same contribution from the same row as the point in the middle and the other rows, no, you're emphasizing the basically the middle row here in the image in the kernel. Okay, will that make a difference? Actually, you have to try it yourself. It's very difficult to say that it will. Okay, you have to actually see it yourself. You have to try it and see if it makes a difference in the particular image type that you're going to work with. Okay, so basically one of the things that we're going to do in the next assignment is basically try to use different types of images. I basically collected a few types of images. Let me show them to you, and basically I'm going to share them with you basically on Blackboard. So basically I chose basically an angiogram image. See, this is an angiogram image. Basically, you inject a dye and basically you take an X-ray image. This is very similar to what you will get in the cath lab. This is basically one of the images that you will get for a blood cell microscopy. Basically, the cells that look different are basically either lymphocytes or white blood cells or whatever. The other ones here are white blood cells, are red blood cells. And basically, in such images, there is a challenge in how to count them automatically. And basically, we're going to discuss ideas about how to do that. This is another image, but it's basically it shows a little bit more cells here. And basically, there's a challenge also of how to compute the number of or do something like an automatic cell counting in images that look like this. This is very similar. This is an Mra angiography, which is basically another type of angiography, but it's done in MRI. In MRI, the advantage, you can actually do Mra angiography without having a contrast agent if you want to. But this particular image actually uses a little bit of a contrast agent just to make the contrast of very small vessels very clear. So basically, you can get something that looks like this. MRA. So basically, this is also one of the very nice images to look at. This is a nuclear medicine image. As you see, it's very noisy, and basically you can probably think about ways of making the image a little bit smoother and basically without removing the details. This is one of the useful images of the retina. Basically, you can get an image of the retina that looks like this. Basically, this is the optic disc where the optic nerve is connected, and basically these blood vessels are very important to detect. And looking at the blood vessels in the retina is very important in such cases as for diabetic patients, just to make sure that there are no basically deterioration of the vascular tree that is associated with diabetes. So this is one very important area. There are some different images that basically the same image might look actually like this because of the different imaging conditions. So basically you can actually think about how to also try to adjust this image to look like the other one. Okay. This is another type of retinal image that is taken with a particular contrast agent. Basically, if you look at this image here, you will see that the blood vessels are dark and the retina itself is basically bright. Here it's exactly the opposite. Basically, you put a contrast agent, it's called endocyanine green, and basically when you do that, you will see the images and you will see the vessels as bright, and the background, the retina itself, the retinal tissues will look dark. So basically this can be very useful. Combining such image with the other one is really, sometimes it's very important. So basically this is another type. This is an image for a skin cancer. Also, it's important to detect the edges of something that looks like this. But actually, the edges here are not very clear as the edges that we were talking about a few minutes ago. It's not like it's a certain level and then it became another level. It's much more complicated here. So basically, it would take a little more processing innovation actually to be able to detect this particular part and basically segment it out of the image. This is another type of skin cancer, and this is an image of the thyroid in nuclear medicine. So basically there are so many different types of images that we can actually try, and we design the kernel that suits each particular type. If you're going to, for example, detect the vessels in the retinal images, we might want to design a particular filter that would be able to detect the blood vessels in a particular way. Okay, and basically it might be an edge detector, a simple edge detector. You might need to add some filtration. You might need to basically look at not only the horizontal edges, the vertical edges, or basically prefer vertical to horizontal, because sometimes vertical edges are associated with the places where the blood vessels go into the optic nerve, and this is going to be a very important criteria sometimes. So basically, depending on the application, you design the filter. Let me show you an example of such designs. Basically, there's a filter called Laplacian. Laplacian, actually, if you have a kernel that looks like this, what do you expect a kernel that looks like this to do, basically? You have here 8, and you have -1, -1, -1, -1. Everything else is -1. Okay? What would a kernel like that do? Basically, you have 8 -1s, and you have only one positive number that is 8 in the middle here. Imagine that you have this Laplacian applied to this area here. This is basically the starting image, basically. We can actually try that right now. We can actually create an image that looks like this and try that ourselves. But basically, let's think about it conceptually first and then apply it practically after that. If I put this kernel here, somewhere here, what do you expect the result to be? If this Laplacian was placed here, can you hear me? Can you hear me?
Yes, Doctor, hear you.
Yes, doctor.
So what do you expect it to be? If I take this kernel here and place it here and try to compute the result. Imagine that these are zeros and these are some other value that is not zero. What do you expect this value? The value of applying this kernel to this area here, this particular black area here. Basically, if you multiply all these numbers by 0, the result will be 0, basically. And even if you put it here, if you put this kernel here, you're going to multiply all these numbers by a constant. So the result would be the same constant multiplied by the summation of this Laplacian kernel. The summation of this Laplacian kernel is what? 0. Because basically you have 8 minus 1s, so it's minus 8, plus 8, so it's 0. So this Laplacian, actually, it's an edge detector. But the point is, it's basically, it can detect the edges anywhere. So basically, you can, instead of getting only the vertical or horizontal edges, you're going to get both edges, both vertical and horizontal. Let's try that. And instead of using the image that we got from the database, we're going to create an image that looks like exactly like the one that we saw here. Okay. So basically, I'm just going to say image is equal to, for example, zeros of 100. Let's make it okay. It's 100. A bit small, 200. Okay, so it's 200 by 200. Okay, and I'm going to have the middle part of it, like from so say 75 to 125. And 75 equal to 100. Let's display that first and see what it looks like. See now, it looks like this. Looks like just a box inside a black area here. When we applied the Sobel, the Brewitt filter, basically the result ended up looking like this, basically. Is that correct? If I apply a horizontal edge detection, should I expect it to look like this, or should I expect something different? Basically, if I look at, it should have actually an edge here, an edge there. Apparently, basically, because we didn't really care about the sign that we came up with here, we should actually put an absolute value here. In order for us to be able to see both edges, I have to have absolute value so that the negative values do not become 0, because actually if you try to display minus value, it's not going to appear at all. See now? Just as I put an absolute value, basically the other edge appeared. And here, if you see here, this is the Brewitt filter. You have an edge that has 2 points. Here, when we use our own filter, it has only 1 point. See the difference? Okay, so what I'm going to do now is basically just design another filter, H3, based on the Laplacian. I'm just going to do it exactly the Laplacian that we just saw. Basically, remember that when we create a kernel here, when we put a semicolon, this means that it's another row. Okay, if I put here, I can actually put it like this, or I can put a column, comma. Okay, this is a comma. Comma means it's exactly the same. Basically, it's a different column. Semicolon means that I move now to a different row. So basically, I'm going to do it exactly the same way it was in the figure. Okay, and then I'm going to have basically I'm going to use that third one. Let me correct that. Here it's Laplacian, so that we remember it. Okay, and here I'm going to basically add it here also. How do you like that? Looks very nice, right? And instead of having to apply two filters, one for the vertical, one for the horizontal, the Laplacian gave us basically both in one operation. Okay, so these kinds of ideas actually are very nice. Just think about a kernel that would actually do a particular function and basically try it. And the only way to judge if a kernel is working or not is just by trying. Is you have to experiment with things. Okay, so the Laplacian we saw here, it gave us something that actually looks like this. It very clearly looks like this. One modification of the Laplacian kernel is that if we just come here and instead of having an 8 here, we're going to have a 9. This 9 means that I'm going to add a 1 in the middle here. 1 in the middle, if you have a filter, basically, maybe you can go here and explain it a little bit more. If you have a filter that looks basically exactly like the okay, and basically if you have numbers here, if you have -1, -1, -1, -1, 9, -1, -1, -1, -1. This will be equal to the Laplacian, the exact Laplacian kernel that we just saw, plus something that would look like this: 0, 0, 0, 0, 1, 0, 0, 0, 0, right? What does this look like? If I look at this kernel that I'm outlining now, does it look like something you know? What does this look like? If I basically take a kernel like this and convolve it with the image, what would be the result? Does this remind you of something? It's like an impulse. Basically, if you have an image and convolve it with an impulse, it's going to be exactly the same as the image itself, the original image. Nothing will change. So basically, if I use a kernel that looks like this, the result will be the result of the Laplacian added to the exact same image that you started with. Okay? Are you with me, or are you lost?
Please again.
Okay, so this basically the kernel that we were talking about, it's basically instead of having an 8 here in the middle like the Laplacian, basically it's going to be the Laplacian, which is basically -1, -1, -1, and 8 here, -1, -1, -1, -1, -1, -1. This is the Laplacian. If I add to the Laplacian something that looks like this, okay, this is basically just an impulse. So basically, if you take this kernel and apply it to an image, basically the application will be basically the result of applying the Laplacian to the image plus applying this additional kernel to the image. This additional kernel basically is just an impulse. Basically just a unit pulse. Basically you have only one in the middle here. This is like an impulse. When you convolve an impulse with an image, you're going to come up with exactly the same image. Let's try it. If you probably confused about it, let's try it. What I'm going to do now in MATLAB is just use this image. We have an image already here. Okay, I'm going to create a kernel here, H4, that looks like 0, 0, 0, 0, 1, 0, 0, 0, 0. Okay, and I'm going to filter the image with this kernel. H4, okay? And basically, I'm going to see what image, the last image would look like. See here, this is the one that was filtered by the impulse filters. It's exactly the same as the original image. Okay, so basically the filter that would look like 0, 0, 0, 0, 1, 0, 0, 0, 0, basically the result would be the image itself. When I apply a kernel that looks like this, it's going to give you the output of Laplacian plus the output of the impulse. Okay, as if I applied this to the image and basically applied this to the same image and basically added these two results together. So basically you would get something that would look like the addition of this plus this. Let's try it. So instead of having the instead of having h equal to this, just this, I'm going to have it equal to this plus h3. Meaning that instead of having 8 here, you're going to have 9. Okay, so let's see the output, how the output looks like. Here it might not be very clear actually, but the edges here should be actually higher, should be a little bit higher. It might not be very clear, but let's try. Maybe what I should do is just forget about image adjust. Image adjust actually sometimes mimics or hides the results. Actually, it doesn't matter. But actually here, it basically, if you add this to that, basically you're going to have the edge here basically emphasized. Might be a little bit clearer here. Basically, it would look like something like this, basically. Okay, you're going to have something that would look like exactly the same original image plus the edge. Okay, so it looks like this. This is called high boost. High boost meaning that the parts in the image that have edges, they will be emphasized. You will be actually having higher intensity. Okay, so basically there are different designs. This is basically just an example of a design that was meant to emphasize the edges here in the image. Let's try and basically instead of having this simple shape, I'm going to go back and use the original image that we just talked about. That's the same exact image, the spine image. Okay, I need to have image adjust just to, because actually the intensity is a little bit lower. Do you see this image? Compare this image here to the original one here. You will see that the parts where the edges are basically emphasized. Okay, so basically see the parts in the middle here. So basically wherever you have edges here, you will see that these edges are emphasized here. The same thing here. See the edges here? Here they are not really very bright. Here they became a little bit brighter. Here also you see some edges inside. Basically these edges are emphasized also. So basically this is a way of emphasizing the parts of the image that have particular edges. Okay, so basically you highlight the parts of the image that have edges and separate them from the parts that don't have edges. Okay, so basically this is an example of how to design a kernel for a particular function. Okay, so basically it depends on the particular way or particular application that you're working with. You can design different kernels, you can design, you can propose a particular kernel for a particular application that might actually make sense to you. Whatever, if you have a logic behind it, it actually can be very useful. Okay, so basically what I'm telling you here is that instead of using the F special, okay, and designing filters using F special, the very limited set of filters that are available for F special, you can actually design your own, and you can customize the filters the way you want, actually depending on your application. One more thing here before we leave this part, we would like to try this on a colored image. Would it be possible to detect the edges of a colored image? Let's try and basically use, if you remember, we had the histology image that we used before. Yes, it's right there. It's histane.png. Okay, let's try and see if it works. Okay, there's a problem. Our image adjustment just doesn't work with the color image. So basically, let's just leave it. Image just has to be used with a black and white, because for the colored image, it doesn't know which one of the colors to use in image adjustment. So basically, you just have to remove all the image adjusts here. Okay. See now here, the edges, of course, look a little bit strange because they are in color. But what you can do is basically compute the compute the absolute value or the grayscale value of the edges. But actually, apparently, we can actually detect the edges here that are present in the image. And here also you can see them, but probably the contrast will not allow you to basically see the clear edges that are there, because the values of the edges are not very high, because the original values of the image, of course, will be higher than those of the edges. This is the one that we talked about. Basically, this is a boost image, the high boost. Basically, what we did was to this is the Laplacian, which computes the edges everywhere. The edges, the vertical and horizontal edges. Here, of course, you see there that most of the edges here are horizontal. Here also it's horizontal. Here you detect the edges in horizontal and vertical directions. Here you feel that this image is a little bit coarser than this one here. You feel that this one here is a smoother version of this one here. Is that right? You feel that as if you basically filtered this image to get this image. Because here you see some of the details that are not present here. Because basically here you emphasize the edges. Whenever you have edges, whether they are inside the structures or around the structures, basically you are emphasizing them. You're adding the edge to the actual image. You're adding an image that looks like this to the original image that looks like this. So basically sometimes it's important, or sometimes it's useful to actually see an image that looks like this, because sometimes the variations in the structures inside might indicate some variations, some particular pathologies. For example, if you look at this part right there, you see something here, you see some variations here, but they're not very clear. Here they are much clearer. So sometimes it's useful to have this high boost filtering applied to the image. Basically, I'm trying to show you several applications, and basically you're going to try different applications yourself. I'm going to prepare some different applications so that you can try them yourself without having prior information about which one should work, so that you can try them yourself and basically get the experience of testing new ideas. And basically it's just a matter of experimentation and thinking about the structures inside the image and which one would work better or work best for a particular application. Do you have any questions? Okay. What I'm going to do now is I'm going to show you how to simulate an image with noise. Okay. There's a function in MATLAB called image noise. Okay. So let's look at the help for image noise. Basically, it takes an input image and adds a particular type of noise, basically either whether it's Gaussian or Poisson or salt and pepper or whatever, speckle noise. Speckle noise is very popular in ultrasound imaging. Salt and pepper, there are some applications where actually the noise might look like this, like sometimes in the nuclear medicine, salt and pepper might be a little bit present there. Gaussian noise is present in any type of imaging, basically. Gaussian noise is related to thermal noise. If you're doing any kind of electronic imaging, whether it's photography, whether it's medical imaging, as long as you have the image signal going through wires, okay, and these wires are not at 0 degrees Kelvin, you're going to have thermal noise. Okay, so these are very popular, and these are the Gaussian noise that we usually encounter everywhere. We encounter them on basically 1D signals, and we encounter them also on images. Okay, so basically these are different types. We can design a particular contamination and basically test filters in order for us to know whether they are working or not. So for the Gaussian noise, for example, we would expect that an average filter would work. Okay, we saw last time for F special, we can design a filter that looks like a rectangular kernel or like a circular kernel, and basically try that and basically see if it works or not. We can try also the salt and pepper. Salt and pepper are very interesting, and I'm going to show you that also because actually it will be the start for talking about the other types of filters, which are the nonlinear filters. Okay. And basically, it will be very clear to us actually when we use the other type of filters, what additional value we can gain from nonlinear filtering. Okay, so what I'm going to do now is I'm going to start with a particular image. Maybe you can start with the black and white first. Let's just keep this image here. Maybe you can just work with these two images. I'm going to read the spine.tif. And basically, I'm going to generate image N, which is image noise, MIM and Gaussian. Basically, Gaussian noise, as you know, adds Gaussian random numbers to the value of the image itself. So basically, if you go here and explain it a little bit more, basically, if you have Gaussian noise, if you have noise in general, we're going to assume, usually, we assume that they are independent and identically distributed. What does that mean? Okay, which is sometimes you call it IID. Okay, independent means that I have this pixel and I have another pixel here, I have another pixel here, I have another pixel here. Okay, each one of these pixels, this is for example x1, this is x2, this is x3, this is x4. Okay, if the original value of this pixel is x1, the noisy value will be x1 plus n1. And x2 plus n2, and so on, okay? If I look at these two, basically n1 and n2 will be Gaussian, but they are actually not related to each other. They are independent Gaussian processes, but they are identically distributed, meaning that basically in the Gaussian distribution, if you remember, it's the bell shape, the original bell shape that we all know. Basically, you characterize it by the mean and the standard deviation. And usually you say that it's sometimes people use this particular notation. It's normal, because Gaussian is a normal distribution with mean of m and standard deviation of sigma. Sometimes people like to use the variance instead of the standard deviation, but actually it's characterized by this, a mean and a standard deviation. But there's a difference between basically having these n1 and n2 as both as Gaussian distribution coming from independent sources and having them from the same source. Having them from the same source meaning that this n1 here is exactly equal to n2 all the time, which is not correct. Usually the noise comes or is added to each one of the points in the image differently. You have, as if you have an image that has 100 pixels, then you have 100 sources of noise. They are all identical, meaning that they have the same mean. Usually you have a mean of 0 and a particular standard deviation, basically that determines, how far the values are apart. Usually the numbers are between -3 sigma to 3 sigma. So for example, if I say that sigma is equal to 1, then the noise will be from -3 to 3. Basically a random number is added to the pixel, and this random number can take any value from -3 to 3. Okay, if this is a Gaussian distribution with 0 mean and a standard deviation of 1. Okay, so basically this image noise function, it basically does exactly that. It generates the random numbers and adds them to the image. And basically, if you want, you can actually change the sigma. Usually for the Gaussian distribution, basically the sigma is the most important. Let's try that and see it for ourselves. So I think we should just comment that for now, so that we don't really get confused by the extra outputs. So image noise looks like this. Basic Gaussian here, you can have it as Gaussian with a certain mean or a certain mean with a certain variance. Okay, so basically let's start with mean, or basically maybe I can just start with the mean and standard deviation so that we have all the values. So let's start with 0 and standard deviation of 1, or basically it's a variance, which is the standard deviation square is exactly 1 in both. So, and I'm going to display these two images together. Okay, so I'm going to have a new figure. Let's also have the, in order for it to appear, okay, it's fine. You can just try it like this. How do you like that? Do you see anything? Basically, the image is gone, basically, right? You don't see much, right? When we added the noise, we didn't see much in the image. Let's improve things a little bit, because the values might be a little bit, let's just say image 1 equals to image adjust, so that adjust values first before we do that. And image 1 here and image 1 here. Let's see if this will improve things. A little bit, okay? It looks very noisy, of course, right? Let's try to change the variance of the Gaussian distribution, okay? So instead of having the Gaussian distribution here, having a variance of 1, we're going to have a variance of 0.1. Looks a little bit better, okay? So let's try to have it as 0.01. Okay. Actually, this looks like a realistic image, a more realistic image. You don't really expect to have an image with much more noise like the ones we just saw before. So this can be actually a very nice image to start with. So basically, when we change the variance, we change the amount of noise that we see in the image itself. How about if we change the mean? Okay, let's just change that instead of just having only variance, we're just going to change that by 10, for example. The mean is 10. This means that basically the noise will be elevated by a value of 10, basically. Instead of being from minus 3 sigma to plus 3 sigma, you're going to end up with something that would be from mean minus 3 sigma to mean plus 3 sigma. So let's see the output. Looks very different. Basically, you added a number that was really large. I mean, it doesn't make sense to have it like this. Basically, you saturated the image. Let's have a smaller number here. Let's just have 1. See, basically, you're saturating the image here. Basically, you're adding a number to all the images. Basically, when you have a mean of 0, it's preserving the image itself. When you have a mean, the noise mean, if it's above 0, then you're adding this value to the whole image, which basically brings the image to be something that doesn't really look nice like this. So basically, let's just have this as 0.1, for example, 0.1, and see. Basically, it's the same image, but you feel that it's a little bit brighter than the original. It's basically, if you look at certain areas, you feel that it's became a little bit brighter than it should be. So basically, usually for the Gaussian noise, if you're talking about the thermal noise that comes from image acquisition through electronics, basically you don't expect the mean to be anything other than 0. So basically you're going to go back to have a 0 mean here. And what we're going to do now is start from this image here and try to recover back an image that would look like this. Okay? We said that maybe the average filter would do that. Basically, this is a filter that we just talked about here. If you have an average here, then you're replacing each one of the points in the image by the average of the 3x3 centered around this particular pixel. Let's try that. So basically, I'm going to take image noise and basically filter it. So let's just say it's image filter 1 is equal to image filter. Because basically the filter is very simple. I'm just going to plug it in there. So image noise and ones of 3. Ones of 3 will give you basically a 3x3 ones. Okay, and then I'm going to try ones of 5, which is going to be just, you know, a 5x5 kernel like that looks like this, and see which one works. Okay, so I'm going to have that as ones here. Okay. I'm going to add these here. So basically, I'm going to display the original image, the noisy image, and the filtered images and see how they look like. There's a problem here. Basically, you see that the image here is saturated. Usually, this is because the way the image filter works is that it expects the kernel to be basically normalized. So basically, if you have a 3x3, it should be divided by 9. Okay, if you have a 5x5, you should normalize it by 25 in order for you to be able to get a normalized kernel. Other than that, you're going to get the summation of the 3x3, not the average, the summation. And the summation will be higher than the original image. We don't want to do that. We just want to keep the original image levels the same. Okay, how do you like these? Are they improved? Please give me your opinion. Do you think that they are improved? Basically, compare an area that is clearly noisy. For example, this area here, this area here. If you compare this area here, this is clearly very noisy. Here, it's a little bit improved. Here, it's a little bit more improved. It's further improved. But do you see any problem? Basically, this is definitely from the point of view of noise, this is definitely has less noise. But do you see any problem in this image compared to the original? If you compare it to the noisy image, then definitely it has less noise. But if you compare this image to the original one, what do you see? What's your comment?
It has some noise.
It still has some noise. Definitely you couldn't get rid of noise. This is very important, right? This is correct, right? Do you see anything else? Basically, if you look at such places where you have edges like here and compare them to here, you feel that this is not exactly as sharp as the original image, right? See here, you feel that this is a little bit blurred, okay? Because basically when you're using a 5x5 kernel, you're basically mixing the pixels together. And mixing the pixels basically will not allow you to keep the edges the same sharp way they used to be in the original image. Okay, so basically here, this is a filtered image. It has less noise than the noisy image, but actually if you look at the original one that doesn't have noise, you will notice that you introduce blurring. Okay, so basically sometimes it's might be useful to use different more innovative kernels, but actually usually you don't expect at all to be able to remove the Gaussian noise altogether. The problem with the Gaussian noise is that they are basically distributed in all the frequencies. Basically all the frequencies of the image will have Gaussian noise. This means that you can never remove it. You can reduce it by using something that looks more like a low-pass filter. Basically, what we did here, the average filter is just a low-pass filter, okay? And you can actually prove that. When we start talking about the Fourier transform, maybe inshallah next time, basically we will know that this kernel actually corresponds to a low-pass filter. So what you're doing here is reducing the noise in the image by removing the high frequencies. And basically, while you're doing that, you're removing some of the useful high frequency parts of the image, which are the edges. The edges are the most important high frequency component of the image. Okay, so basically, if you have an image that looks like this, you have to actually decide on which kernel that you're going to use based on the kind of noise you have. And basically, you have to experiment. You cannot basically just say that an average filter 3x3 should work. No, you have to try it yourself. And you have to see if it actually works, or if there is any particular modification that you have to add, or whether you have to, for example, do something like maybe changing the size of the kernel, or using something that would boost the high frequency components. Let's try if we use the high boost here. If you use high boost with this image here, let's see how it looks like. So basically, if I take this image, basically the IMF2, and basically I'm going to apply the image boost, the one that we just saw here. Okay, let's just take it from here. So I'm just gonna put this as 9 here, so that it becomes boost, so that we see if the edges that were blurred in the original image would become a little bit clearer here or not. Let's just say this H5, and this will be IMF3, and this will be H5 here. Okay, let's try that. It didn't work at all, right? Basically, this is the one that that got filtered. Oh, actually, I'm sorry. Actually, I filtered this one here. Actually, I should filter the not the noisy image, the one that we got from IMF2. just to see if I'm just going to filter the last one. Basically, I'm going to start with this and try to have a high boost of this one so that see if we can recover the edges or not. Actually, it didn't work. It also didn't work because basically when you try to boost the edges, you're going to boost the noise because basically the problem is for filtration, in order for it to work perfectly, you have to have separation between the range of frequencies of the original image and the range of frequency of noise. What you have here, basically for a filter to work, you assume that this is a frequency component, basically. This is the frequency axis here. Basically, what you have here, the frequency, you assume that the image itself has something here that is actually true. And you have some noise that basically that is unwanted somewhere here. Okay, so basically if you try to have a filter that would actually select most of the true and basically remove this part here, you'll get something that would look okay. Okay, so as long as you have an area of overlap here, you will never be able to recover this particular area from just filtration. What we have here, we have white noise. White noise is Gaussian noise, is normal distribution, is basically all the same, okay? The problem with normal distribution is that basically the noise looks like this. This is infinity and this is minus infinity. So whatever you do here, you're not going to be able to remove it at all. What you try to do is basically minimize the amount of noise that is present in the image, which basically, if you limit the bandwidth of the image, you limit the amount of noise that you're taking. So basically, when you do a filter that looks like this, you're basically removing all the other part of the white Gaussian noise. So you're getting something that is a little bit better. But the amount of noise here, the part of noise that is here, will never be removed. Okay? In order for me to just demonstrate a little bit more, if you have at frequency, for example, 100 hertz, for example, okay? If you have the true signal as, for example, X, and the noise is N, these are numbers, just numbers, okay? X is equal to 100, and the noise is equal to -5, for example, okay? The summation of the two will be 95, okay? In the filtration problem amounts to trying to get the 100 and the -5 out of the 95. Can you do that? This is like an equation of X plus N equals to 95. Solve for X. Can you do that? Can you solve a problem like this? Can you solve a problem like this? Just one equation in two unknowns? Can you do that? You cannot. So whenever you have an overlap between the image frequencies and the noise frequencies, you're not going to be able to recover the true image exactly the way it was. You're going to get something improved, but you're not going to be able to get exactly the true image at the end. Okay? Okay, let's try that. Same example here with an image, a colored image. So basically, I'm just going to change that to the histogram image and see what happens. The histology image. Okay. And let's remove the other last part here because it's not useful. Okay. Image adjust. We don't want to have image adjust. Okay. No image adjust with color. We got that comment like 1,000 times today. Okay. Still work with the color. Is there anything different? Stain. Oh, okay, okay. Sorry. This image 1 should be equal to image. See here, this is the original one. This is the noisy one. Maybe it's not very clear. Let's amplify it, zoom in. See here, it's very different, right? So you can see the difference between these two, right? See the difference here? It's very clean. If you look at a certain area here, you don't really see much variations. Here you see very clearly you have noise here. Okay. So basically you can also have colored images that are contaminated with noise. Definitely we do that. When we filter that image, we get something that looks like this. Actually, it looks improved. It looks very good, actually. This is not bad. If you compare this to the original, to the noisy image, this definitely looks good. But if you compare it to the original here, you will see that some of the details are missing. Basically, it's not as sharp as the original one. If you look at the 5x5, this is the kernel, the 5x5 kernel, you will see that it's much more blurred. This is the blurring here is very clear. So basically, definitely it's very smooth, but actually it's very blurred. So there is a trade-off between the size of the kernel and basically you have the trade-off between the quality of, or the signal to noise ratio, the removal of the noise, and the blurring of the image. So basically, whenever you remove more noise, you're gonna introduce more blurring, okay, and vice versa. So you have a trade-off there. You're trading off noise with sharpness of the image. You get more sharpness or less blurring when you have more noise, and the other way around. If you want to remove noise, you are going to have to sacrifice the accuracy or the resolution of the image. You have any questions? Okay. Now I'm going to introduce another type of noise. Basically, I'm going to just copy everything here and just use a different type of noise. Okay. Let's just put this as Gaussian noise. And basically, you're going to have here salt and pepper noise. Salt and pepper, basically, it's meant to indicate that salt and pepper, basically, salt is white and pepper is black. So basically, the image will be contaminated with basically black and white dots. Let's start with the black and white image first. And basically change this Gaussian to salt and pepper. I think it's written. Maybe you can look at the help. It's salt and pepper. Okay. And it doesn't really need the parameters, at least for now. So we're going to delete those parameters. And let's just have another figure. Okay, Salt and pepper, let's see how it looks like first, and then, okay. Okay, maybe you should have the image adjust first, because it doesn't look very good here. For the black and white, it's very useful to use image adjust whenever possible. So let's just have it. Okay. So do you see the kind of noise that you see here? Maybe I can magnify it and show it to you, because actually here you see the white dots, but you don't see the black dots. But actually, if you zoom in, you will see it very clearly, actually. See here now, you have black dots and you have white dots. It's basically as if you threw like salt and pepper on the image. Basically, you have the white salt pixels and the black pepper pixels. And you need to remove these. And basically, if you use exactly the same filters as you saw, you can just run it again. It's very clear that it's not really working. Basically, for the 3x3 here, you see that you still see the pixel here, right? It's not really very nice, actually. Let's maybe zoom in and see it again. See here. You can still see the pixels. You can see the noise. It's less than before, but actually you can still see the grains. You can still see the points that are inside the image itself. And basically, if you do that, basically if you look at even a 5x5, it's still also present there. So apparently this type of filtration is not very suitable for the salt and pepper noise here. In order for us to think about how to remove such very annoying filter, such a very annoying noise, actually, we have to think about something that is not linear, really, because actually what you have here is something that is very different from the surroundings, and you have to basically select it based on a criteria that is not linear. For example, if I told you that how to recognize, basically, if you have a white pixels here, or if you have a even white or black here, how do you recognize the black pixel in this neighborhood? How can you do that? If I told you whether there's a black pixel here or not, what operation would you use to recognize that black pixel? If I have a kernel, see here, basically, this here like a 3x3 right there, okay? And this is a color, this is a color. This is only black. How do you recognize that this pixel is very different from the background?
Comparison between this pixel and the
yes,
other.
comparison. Yes, comparison. What type of comparison operation or comparison operator would you use? It's right. It's very right. It's comparison. It's exactly comparison. Okay. How about if you use a maximum or a minimum? Okay. If we basically take the maximum of these pixels, okay, or the minimum of these pixels, would you be able to recognize that this pixel is different? How about if you compare this pixel to the mean of the surrounding pixels? Would that work? It definitely would work. If you, for example, if I take this pixel and compare it to the mean of all the pixels around it, would that work? Actually, it should. Another operation, if I take the 3x3 kernel here, or the 3x3 region here, and just do sorting, just sort all the values inside the 3x3, and look for this value in that sorted list. Would it be at the beginning, at the top, or at the bottom?
At the bottom.
At the bottom. How about if you have a white pixel?
At the top.
At the top. So basically, it means that if I take a pixel value in the middle, it would definitely remove that, right?
Yes.
Okay. This is one type of nonlinear filters called median filtering. Median filtering. Basically, what we saw, what we were just using is just an average filter. Average basically is the mean filter. Basically, you're replacing the value of the pixel by the mean of the surrounding pixels. How about if we remove the mean and replace it by the median? Basically, the difference between the mean and the median, it's a very important difference and very key difference, basically. Is that the median is much more robust to outliers. Okay, so basically, what's the meaning of robustness to outliers? If, for example, I have 5 numbers, okay, and these 5 numbers are 1, 2, 3, 4, and 1000. Okay, do you have a number here that looks like an outlier? Outlier means basically a number that is very different from the other elements in the same list. So do you see an outlier here? Yes, this is definitely an outlier. This is very different from the other 4 numbers, right? How about if you compute the mean? If you compute the mean, what's going to be the mean of this? Around what? Around what? Basically, 1000 plus 4 plus 3 plus 2 plus 1. Say it's 1000, approximately 1000. Divided by 5, it's going to be almost 200, right? How about the median? What would be the median? The median is the number in the middle. Basically, I have to sort them, already sorted, and basically take the number in the middle. If I have 5 numbers, I take number 3. If I have 7 numbers, I take number 4. If I have 101, I take element number 50 or 51. Okay, 51 in the middle. Just take the number in the middle. So the median here would be what? Would be 3, which is actually much closer to the most of the numbers than the 1000. So basically, it's exactly the same application we have here. If we have a pixels, a list of pixels that look like this. If you have, for example, 10, 11, 15, say 20, 17, and for example here 100, and this is also 13, 14, 16. If I have something that looks like this, the 100 here is definitely an outlier. The problem with outliers in the mean is that they are going to drive the mean very high. They are going to give you values that are very far from most of the other values inside that same kernel. Okay, if I look at this, you have 11. If I wanted to sort these numbers, 11, you have 10, of course, first, 11, and then you have 14, you have 15 twice, and you have 16, you have 17, you have 20. Okay, and you have the 100. Okay, you have 9 here. 1, 2, 3, 4, 5, right there. 5 would be 15. So the median would be 15. So if I do median filtration, you're going to end up with a value here that looks like 15. If you have the mean, you're going to have basically 100. You're basically going to have a number that is basically shifted by 100 over 9, which is really a large number. So basically, instead of having 15, you're going to end up with something that is basically maybe close to maybe 27 or so, something like that, which is much different from all the other values here. So whenever you have an outlier, a number that is really large or really low compared to the other pixels around, you're going to end up having a problem with the mean. If you use the median, basically you're going to get a much better result. Let's try that. There's a function in MATLAB called median filter. I think we can get it. I think it's mid-filt too, I think. Let me try it. Okay. It mid-filt 2, so that it's medium filter 2. Look at the help. Yes. So basically, it's if you just use it like this with the image inside, it's gonna assume that you have a 3x3. You're gonna do a 3x3 medium filtering. If you use it like this, then it's gonna use a kernel of m by n. If I use it, for example, m is equal to 4 and n is equal to 3, then it's gonna take the median of the values in a 4x3 area and basically use it to compute the output and so on. Okay, so basically we can basically just try it with the 3x3 first. So I have IMF3 is equal to medium filter of image n, with the one with the just image n, and that's it. I'm just going to display it. That's it. How do you like that? This is the outcome here. Can you see the difference? Basically, let's basically see. This is a noisy one. This is the one 3x3. This is the one 5x5. This is the one with the medium filter 3x3. It's not even 5x5. How do you like that? Looks really nice. You don't even see any trace of the salt and pepper noise. Do you see any trace of the salt and pepper noise? I really don't see it.
No.
It's basically it's all gone. So basically, it's the design of the filter that would produce the results that you want. Basically, some types of filters, no matter how you try, how you change the parameters, will never give you something that would be acceptable. If you use a different type, or basically I use a suitable type to the particular noise that you're using, you're going to end up with a really great result that looks like this, as you saw here. Looks much better than any of these other ones. Let's see if it works with colored noise or colored image instead of the black and white. See if it works with the color as well. So we'll just have to remove the image adjust and see if it works. Okay. Okay, there's a problem here. Medium filter doesn't work with colored images. Okay, so what can we do? So it doesn't work with colored images, but actually what we know is that the colored image is just 3 black and white images, right? So we're gonna have to do something a little bit tricky here. Instead of just using the image filter, medium filter right away, I'm going to have image F3 is equal to image noise, first of all. Just start with that, just to have an image of the same size as a noisy image. And then I'm going to have 3 filters, image F3 of the first color will be equal to medium filter of the same exact one. Okay, medium filters. Okay, I'm not sure if it works or not, but sometimes it actually, when you have one here, it's gonna still recognize it as 3-dimensional, as n by m by 1. Okay, but let's try if it works or not. But I'm going to do that basically for the 3 colors. Just apply the medium filter to each one of the 3 colors. Let's see if it works. Actually, it worked. Which one is, I think it's figure 3. Yes, it's figure 3. See now, the noise is very clear here, right? This is salt and pepper noise, but actually the salt and pepper, because it's ones and zeros in each one of the colors independently, then you're going to end up having something that looks like this. If the one is in the color red, you're going to see a red dot. If it's in the green, it's going to be like a green dot. If it's in the blue, it's going to be like a blue dot. If it's basically black, any one of them, you're going to have a different color image. Here, actually, it's not that bad for the other, because of the color variations here. It's not bad. Actually, the filtration here, the 3x3 average filter is not bad. It doesn't look much. It's not as bad as the one we saw actually in the black and white. The 5x5 is still blurred, but actually this is definitely the best. This is a medium filter. It looks almost exactly like the original one. Okay, so if you compare this to this for that, this is the medium filter. Go ahead.
There is no maybe there is no effect on the sharpness and blurring. Is that true or
actually, not? Actually, you see that if you compare this to that, you're gonna see some slight blurring here, but it's acceptable. It's not very bad. But actually, you can see it. You can see that this is not as sharp as here. Maybe you can pick an area. Maybe look at this part here and this part here, or these areas. Maybe I can magnify it a little bit. See here, they are not as sharp as the original one. The original one look a little bit sharper here. You actually have to look at them in bigger picture, but actually there's a slight blurring here, but it's not very significant. It's not as significant as the average, because the average actually by definition changes. Basically, the blurring is by definition is just averaging. Okay, when you use something that is a nonlinear like the medium filter, it usually avoids some of the problems of averaging in that regard. So basically, medium filtering actually it works. It basically works. It should work in such applications as salt and pepper noise. And basically, this will be the start to our nonlinear filters. The medium filter is a nonlinear filter because, as you saw, if you want to have a linear filter, you have to have the filter basically exactly as defined, exactly as this equation here. You produce the output as a linear combination of the inputs. This is the input image. You basically, A and B and C, these capital letters are all basically constants. Okay, and you have a weighted average of the original image pixels in the output. Okay, and they are added together. For the nonlinear filter, you don't do that. You either just take these numbers and do a nonlinear operation like median, like maximum, like minimum, things of that sort. And basically, whenever you use a nonlinear operation, you're going to end up with a nonlinear filter. Or you can basically do the same thing here with a weight. You can also basically multiply these numbers here, but instead of adding them together, you just combine them with an operation that is nonlinear. Okay, so basically, I think probably we shouldn't start on that today because you still have the first assignment. Inshallah, next time we're going to explore the operations that we are going to apply on basic nonlinear operations like morphological filters. Morphological filters are among the most important filters that are basically being used practically. And you will find that you can use them in a variety of applications. You can basically, they are very useful and basically not just for things like the medium filter. Basic medium filter is basically, you can consider it as a morphological operation because it's a subclass of it's a nonlinear operation, very similar to what you would do with the morphological operations. But the other operations can be used to basically, if you have an image that has a disconnection somewhere basically you have, for example, a blood vessel that is going, and because of noise, you actually saw that this blood vessel was disconnected somewhere. You can very easily reconnect it using a morphological operation. Okay. So next time, inshallah, we're going to talk about the morphological operations, and hopefully we'll get to discuss at least the theory of two-dimensional Fourier transformation, and inshallah work on the part of MRI image reconstruction. So do you have any questions about what we covered today? If you feel that you have some more questions on the assignment and you don't feel that you can submit the assignment before next lecture, we can actually postpone it for 1 week so that you can ask me more questions next lecture. Would you like to do that? Would you like to delay the assignment for another week? Any answers? Okay, so I'll assume that you don't have a problem with submission in the deadline. Let me just emphasize that it's not a problem if you delay a little bit. Basically, if you have a deadline and you submit after the deadline, it's still okay. The most important thing is for you to understand what you're doing, okay? So if you delay the submission of your assignment, it's fine. So those of you who can submit before the deadline, it's fine. For those of you who will delay, it's still gonna be fine, okay?
Okay.
Okay, so inshallah next time, we are going to have our session start at 4:30, inshallah, on Wednesday. Okay?
Inshallah.
Okay, we're going to start with the part about the morphology and continue on, inshallah, with the part about the Fourier transform.
Inshallah. Thank you.
Please, next time, if you have any problem with any of the parts that we covered before, let me know, please, okay? We are not in a hurry to finish a particular amount of material, okay? We're not like an undergraduate course. If you want to repeat a part, if you want to repeat the whole lecture, it's fine with me, okay? Having a fewer topics with more understanding and more ability to apply these topics would be actually much better. You are going to be basically much more useful for you. The target of this course, or basically all graduate courses, is to help you in your thesis. When you start on your thesis, you want to have some tools that you acquire during your courses. Okay, this is the most important thing. So your most important goal from this course should be to acquire tools that would help you in your thesis. Okay, so basically make sure that whatever you're taking, you can basically use later on your own. Okay. Okay, so inshallah, I'll see you next time. Inshallah, I'll post the material from today's lecture on Blackboard, and I'll see you inshallah next time, next Wednesday on at 4:30 inshallah. Okay.
Okay.
Okay. Good luck inshallah.
Okay, inshallah.
Sure. Shukran. Assalamu alaikum.